Good evening, everyone. My name is Andrew Fracknoy. I'm the astronomy instructor here at Foothill College, and it's a pleasure to welcome everyone here in Smithwick Theater and everyone listening or viewing us on the web to the 12th annual Silicon Valley Astronomy Lecture Series here at Foothill College. This lecture series is sponsored by 4 organizations: the astronomy program at Foothill College, the Astronomical Society of the Pacific, the SETI Institute, and the NASA Ames Research Center, and we're very grateful for their help in both putting on and publicizing this lecture series. The lectures are available, thanks to a generous donor, on the web in both audio and video format. And if you're listening to us on the web, we encourage you to go to the website and take a look at some of the past lectures where distinguished astronomers have talked about some of the most exciting topics in modern astronomical research. Tonight's lecture is entitled "The Ultimate Fate of the Solar System and the Music of the Spheres." A grand topic, and we have a grand speaker to tell us about it. Dr. Gregory Laughlin is a professor of astronomy at the University of California at Santa Cruz. Before he went to Santa Cruz, he worked as a planetary scientist at NASA's Ames Research Center. He's a leader in the field of finding planets around other stars. He's actually the co-investigator for the Lick-Carnegie Extrasolar Planet Survey, which has been responsible for many of the 500 planets that we now know orbiting other stars. He's also an expert on the long-term future. What a nice thing to be able to say about yourself. I'm an expert on the long-term future. We wish more of the Senate and Congress were experts on that subject. He has dealt with the ultimate fate of the Earth, the solar system, the Milky Way galaxy, and the universe. He is also the co-author of a popular book on this subject called The 5 Ages of the Universe: Inside the Physics of Eternity, a book I really recommend to you. We asked him tonight if he would speak about the long-term future of the solar system, the sun and its family of planets. And he told me that the last time he was asked to talk about this subject, he talked about it with Philip Glass, the composer. So we hope that you're going to be as good an audience as he was, and it is for me a great pleasure to present to you Dr. Gregory Laughlin.
Thank you very much for that kind introduction. And it is somewhat daunting to look out onto an enormous theater filled with faces. Astronomers usually don't sort of have that sort of audience in front of them. So hopefully I will not disappoint. So I'll start with a slide that you can barely see. This was taken a little while ago just outside of my window at home in Santa Cruz. And you can see that the dominant thing on this picture is the 2 power lines in the lower right-hand corner. And I don't know if you're in the back whether or not you can see the crescent moon right there. And then more importantly, all the way up in the upper left-hand corner of the screen, you can see a dot. Can you guys see that? Can you see the dot? So that's Venus. And this picture I put up because I wanted to give a sense of the fact that the solar system doesn't really impinge into our daily lives to a great extent. We, of course, are extremely familiar with the Earth and everything that goes on the Earth, but we don't really have a sort of a visceral sense of the solar system. And in order to talk about the fate of the solar system, I felt that it was important to try to establish a sense for what's out there. This was taken with a 5 megapixel camera on a zoom of just a slight bit of zoom. And so if I go in and show the highest resolution in the actual JPEG image, then Venus is up there on the upper left-hand side, the moon is down there in the lower right. I've just zoomed in a little bit. You can see the digital noise from the camera. And what you can see, which I find actually kind of profound, just with this camera, is that Venus is not a point. At this resolution, you can see, if you sort of strain your eyes, you can see that Venus is a half-illuminated globe. It's very tiny. It's very, very hard to see. But you can just barely make out the fact that Venus is a world. And what's interesting is that our own eyes are not quite, we don't quite have the resolution to see that. If our eyes were twice as good as they actually are, then we would be able to see a tiny crescent Venus. And that would have very much changed, I think, the history of astronomy. The fact that the planets can't be seen as individual worlds by the human eye made it more difficult to figure out what was going on. But they're just slightly beyond that ability to see with the naked eye, that Venus is a world, and we know that it's a world nearly the size of our own. So to set context, we're always very familiar with the sort of everyday surface of our lives. You know the route to the store very well. You know the route to work. You're very familiar with your backyard. And what I always enjoy is when we fly out of San Jose, you see, as the airplane climbs up out of San Jose, you see the sort of bay spreading out beneath you, and you get a sense of how the world that you are familiar with in your everyday life, you get a sense of how that world connects to the planet as a whole. And as you fly up to 35,000 feet, you're just barely high enough that you really start to get a sense for the curvature of the Earth. You can sort of imagine that you're on the surface, you're just above the surface of a giant sphere. And some of the most remarkable images from the entire last 100 years were, of course, the pictures that the Apollo spacecraft sent back on the way to the moon and on the way back from the moon. And this is one of my favorite pictures. This is from Apollo, I believe, 15, coming back home. And you can see California, Baja California. You start to get the sense of the Earth as a planet. And then, of course, there are the views which show the Earth fully in the field of view. One of the most amazing kind of transcripts, moments in the entire Apollo program was when the Apollo 8 astronauts, for the first time, left low Earth orbit. And you can hear the shakiness in their voice as they say, I can see the entire Earth. That was a watershed moment in human history. And that entire Earth, we're now beginning to see that in the same sense as we can see sort of Venus through a small telescope, as a world hanging in space on its own. Now, the sun, it's hard to get a sense of how large the sun is because it's too bright to look at with your naked eye, except for the times when it's low on the horizon. If you look at this picture right here, this is a picture of the rising sun, actually, and it's not a particularly bright screen, but if you look right here, you can see this small, perfect black disk. And I guess you actually can't see it. You'll have to take my word for it. This was taken during the transit of Venus in 2004. And during that moment, the size of Venus is sort of projected against the entire orb of the sun. And so you get a sense immediately for the fact that the sun is much, much larger than the planets. The sun, 100 Earths lined up across would fit the size of the sun. And once we have the sun, we can sort of start to get a sense for the real scale of the solar system. So I've talked about the Earth briefly, and what I want you to do is if you imagine that the Earth, the entire Earth, is shrunk down to the size of a grain of sand, that corresponds to a demagnification of roughly 100 billion. If you shrink the Earth down by a factor of 100 billion, then it becomes the size of a grain of sand. About 100 sand grains will line up across the face of a dime. And so I can make a scale model of the solar system at a 1 to 100 billion scale by taking a dime and holding the dime about 2 arms lengths away from a grain of sand. And that always strikes me as sort of remarkable because at that scale, it's very clear that there's not very much in the solar system, right? Everything that's going on here seems to be such a big concern, but it's kind of nice to think about the scale model of the solar system where the sun is the size of a dime and the earth is a sand grain. It puts everything in perspective. And to sort of slow your roll even more, you can make an animation of that or a demonstration of the orbit of the earth. And that demonstration simply consists of me sitting here, standing here for a week. And after a week, if you came back, my hand would have moved 1/52nd of the way around the dime. And so at that scale, there's just very, very little going on. It's a very calm, it's a very sort of placid, uneventful solar system. The other planets in the solar system, it's good to get a sense of what the inventory is. Our Earth here is now plotted to scale in this picture, perfectly to scale against some of the other objects in the solar system. This is Jupiter here on the left. Neptune is about 4 times larger than the Earth, and Jupiter has roughly 10 times the diameter of the Earth. 319 Earth masses would fit inside of Jupiter. Neptune is 17 times heavier than the Earth. These are enormous planets. Here's a picture of Pluto. This is the picture, the planet that Mike Brown is responsible for doing in. And you can see that it's quite small in comparison to the size of the Earth. And so when we talk about the fate of the solar system, when we talk about the solar system as a whole, we want to think of the gas giant planets, Jupiter and Saturn, the ice giant planets, Neptune and Uranus, and then the terrestrial planets, Mars, Earth, Venus, and Mercury. And this is where the terrestrial planets were 20 minutes ago or so in their orbits. This was the plot of the inner solar system this evening at 7 p.m. Venus right now is coming close to coming between the sun and the Earth. Because Venus's orbit is slightly tilted with respect to the Earth's, it won't go in front of the sun as seen by the Earth this time around, but that will happen again in 2012. That's a conjunction between Earth and Venus is when they're in the line. And so the planets go around and around. The outer solar system, I've plotted here. Here's the whole solar system. The inner planets are all bunched in. Neptune is 30 times farther from the sun on average than the Earth is. And so if you plot the inner solar system, it's all bunched up. Jupiter, Saturn, Uranus, and Neptune fill up a much larger region. If this dime is the sun, then Jupiter is the size of a small sort of BB, and that would be 5 full double arms lengths away. So Jupiter would be about halfway across the stage at the scale where the sun is a dime. And the question that has sort of interested people for a long time, it was clear, even in antiquity, that you could predict the motions of the planets, that there was a regularity in the orbits. And how that regularity worked, why the planets are going around the sun, was first understood by Isaac Newton, who realized that an orbit is a state of continual free fall. Let me explain what that means for people who haven't thought about this. If I were to take this dime and just let it go, then it falls on the floor. And if I take the dime and give it a small sideways push, then it makes a parabolic arc and falls at a point slightly over here. You can imagine as I start throwing the dime harder and harder, it will arc farther and farther and land further and further down the stage. I can eventually throw the dime so hard, well, I can't do it, but one could imagine taking the dime and throwing it so hard that as it falls, the Earth's surface begins to curve out from underneath it. And so it keeps falling and falling, and yet the Earth, because the Earth is a sphere, the surface keeps curving out from underneath it, and the dime would just go whizzing around the Earth, always falling, but always missing the Earth because the Earth manages to curve out underneath it. Isaac Newton realized that that's what's going on, that that's why the planets are orbiting the sun. They are all attracted by the gravity of the sun, and they are all in a state of continual free fall. For the last 4.5 billion years, the Earth has been falling around the sun, and yet never manages to actually strike the sun. It's a remarkable watershed realization. Here's an actual woodcut from Newton's famous Principia, which shows exactly what I was just talking about with the dime. Here Newton is imagining building a large mountain on the surface of the Earth and launching projectiles sideways with greater and greater speed. Once you send them at exactly the right speed, then they just fall continuously around and around and around the center of the Earth. Now, the orbit that we're describing here is basically a circle. But we know that the planets orbit the sun in ellipses. An ellipse is an interesting figure. If an ellipse is an ellipse with, we say, eccentricity of 0 is just a circle. And as an ellipse becomes more and more eccentric, we say that its eccentricity increases. Now, I know this is a non-technical talk, but the idea of eccentricity is something that's important to sort of keep in mind for the things that I'm going to talk about. So I'm kind of going to go through it in a little bit of detail. This right here is a perfect circle. The solid line here is a perfect circle, and I have drawn on top of the circle an ellipse with an eccentricity of 0.2. It looks just like a circle that's been taken and shifted to the left a little bit. But it's actually not quite a circle. It's slightly squashed. And a planet which is on an orbit with an eccentricity of 0.2 behaves in sort of an interesting way. These dots here are equally spaced in time. And so you can see that here the dots are spaced more closely together. The planet is moving more slowly through this part of the orbit, and it's farther from the star, which is at the focus of the ellipse, than it is here, where the dots are more widely spaced and where the planet is moving more rapidly. This eccentricity of 0.2 is a pretty modest ellipse, and that actually corresponds to the most eccentric orbit in our own solar system planets. This is the planet Mercury. You're hard-pressed to tell it apart from the moon. This is Mercury. Mercury has an orbital period of 88 days and an eccentricity of 0.2. Its orbit looks just like that figure that I've shown. Now, eccentricities can go above 0.2. Here's an eccentricity of 0.4. Now you can start to see that the orbit is definitely non-circular. You can see that there's a significant difference in distance between the far point and the near point from the focus. And you can see that it's definitely going faster through this part than it is through this part. Recently, we've started finding extrasolar planets that have eccentricities that are quite high. Here's an ellipse with an eccentricity of 0.6. You can see how close it gets to the focus there. And the planets that we're discovering are often on extraordinarily eccentric orbits, and often are in orbits that are much closer to their parent stars than the planets in our solar system are to the sun. Here's a computer simulation of an extrasolar planet that's on a 5.6-day orbit. And this extrasolar planet, because it's so close to the star, it's just completely blasted with light from the star on its day side, and even on its night side. This is a giant planet like Jupiter. Even on its night side, the storms are so hot that they are literally glowing with their own light. They're like a barbecue grill. This is a picture of a barbecue grill that I've taken. The entire planet is sheathed and swathed in storms that are having winds of order 6,000 miles per hour and which are glowing with their own radiation. These are the kinds of worlds that are turning up, and many of these worlds have very high eccentricities. This is a computer simulation of that planet that I was just showing. This planet is on an eccentricity of 0.5 orbit, and so every 5.6 days, its orbital period is 5.6 days, it comes very close to the star, it gets a blast of heat from the star, and then these storms are continuously being driven around the night side of the planet. The planet is continuously, for billions and billions of years, just being toasted and blasted by the heat from its parent star. And it has a highly eccentric orbit. The most eccentric orbit that's been found so far belongs to this planet HD 80606b. And this planet has an absolutely crazy orbit. I've taken the inner solar system, I've taken Mercury and Venus and the Earth, and I've plotted them to scale, their orbits to scale, and compared with the orbit of this crazy planet, HD 80606b. HD 80606b spends most of its time out at a distance which is not very different from the Earth's distance from the sun. It's a little bit closer, but then every 111 days, it comes racing through for a very, very close approach to its parent star. I'm sort of a fan of low-tech, high-tech things. And so what I did is I took my camera, the same camera that I used to make that picture of Venus, and I plotted the orbit with an eccentricity of 0.9 on a piece of paper along with a circle for comparison. And I took a kumquat and I put the kumquat at the center of the circle and at the focus of the ellipse. And then I took a peppercorn and took 100 pictures, one after another, and then animated them in iMovie. And so what this shows is the actual orbital motion. Right? It shows how when the planet is far from the star, it's moving slowly, and then as it comes in close to the star, it goes whipping through. So it's a crazy year, right? This is an absolute disaster if you're on this planet. You're sort of hanging out a long way, and then you come racing in. The star swells to look 1,000 times larger in the sky of this star than the sun looks in the sky of the Earth. And you can see that I did a pretty good job, but you can see my finger with the tweezers comes in on one of those frames. It was just like trying to get all 100 of them was a bit of a stretch. So on this planet, another thing you can do is do a more high-tech approach. And you can imagine simulating the weather on this planet as it goes racing through its close approach with the star. And imagine that you're viewing that weather from a space probe which is actually orbiting the planet itself. So we made a simulation of what it would look like if you're in a space probe orbiting this planet as it goes whipping past its close approach with its parent star. So that's the next animation here. Here the planet, you see the various crescent phases. That's the night side, it's getting heated up. That was when the blast of radiation hit, and the whole planet starts to ring like a bell. There are storms that are basically shock waves that are ringing around the planet and slowly echoing down as the planet basically goes out to the far point of its orbit. And here you see it just as a small crescent. Eventually, at the very end of the animation, the probe, which is in orbit around the planet, comes back in for one last close approach to the planet. The planet kind of comes up, and that's the last part of the animation. So the discovery of the extrasolar planets has given us a sense that planetary systems can be a lot crazier and a lot more dramatic, a lot more eventful than our own system. You know, when I was just showing you those pictures that show where the planets were at 7 o'clock tonight, planetary orbits are all relatively circular. Mercury has the highest eccentricity, but it's only an eccentricity of 0.2, and they're well spaced. You have the terrestrial planets close to the sun. You have the giant planets further out. Everything is quite orderly. So Newton, when he made his theory, Newton realized that the gravity is universal. And so not only does the sun pull on the Earth and cause the Earth to orbit the sun, but the planets also pull on each other. So Jupiter exerts a gravitational force on the Earth, Earth exerts a gravitational force on Venus, and the whole system is sort of marching forward in time with everybody pulling on everybody else. Now, the strongest force by far is the one that the sun exerts, and that's keeping the planets in their more or less perfectly eccentric orbits. But the forces between the planets are perturbing that idealized picture. And Newton wanted very, very badly to understand how that worked. All through the 1600s, it was clear to people who were making observations, it was clear that the orbits of the planets weren't quite perfectly explainable. It seemed that Jupiter was steadily spiraling into the sun, or closer to the sun, and that Saturn was steadily spiraling outward. Newton wanted very, very badly to understand how that worked in terms of his theory of gravity, and he tried very hard to do that. So what I'm going to do now is, with this idea of the planets pulling on each other in mind, I'm escaping from my PowerPoint, or my keynote talk, and I'm going to show a piece of software that allows us to actually push the orbits of the planets forward. So I'm going to open this up. This is a map of our inner solar system. And this software you can download from my website and play around with it yourself. But what you see here, and again, I know that this is a non-technical talk. It doesn't immediately look very good for a non-technical talk when there's all this stuff on the computer screen. So please bear with me. This right here shows the positions of the planets in their orbits. And what this software does, among other things, is it takes into account the fact that the planets are being pulled on by the sun and are orbiting the sun, but also takes all of the gravitational interactions into account as well, and marches forward in time. And so you can do that if I go here to orbital evolution. I can say I'm going to look at what is going to happen to the solar system over the next 10,000 years. I just need to get this so it opens up. There we go. I'm going to say that for the next 10,000 years, I'm going to look at where the orbits of the planets go. And I'm going to plot the positions of the planets in their orbit once per year. And so you're going to see a movie of the planets marching forward in their orbits for 10,000 years. And there's going to be a plot here. And what this plot is showing are the eccentricities of the 4 inner planets in the solar system. So I'm racing through time here and just integrating thousands and thousands of years. So it's sort of like watching a car wheel and seeing it sort of go backward as the car wheel moves forward from the strobing effect. This is marching the solar system forward for a total of 10,000 years, and it's not a very exciting demonstration, right? You can see that the orbits, 10,000 years in, look almost exactly the same as they looked 10,000 years previously. And the shape of the orbits are all basically flat. The Earth has a small eccentricity, that's this blue line right here, and it's just maintaining that small eccentricity. The planets are pulling on each other in the solar system, but it doesn't appear that very much is happening. So I've been sort of interested in alternate ways of kind of getting a grip on this idea of planetary stability. And so one way to imagine that is not to look at the graphs, which are not necessarily interesting, but to try to make a signal that you can hear with your ears. This signal right here is the motion the line of sight motion of the sun as the planets go around it, as the inner planets go around the sun. And that waveform there can be turned into something that you can hear. So I've done that. So what I want to do is play a couple of these waveforms. So I have a whole list of things that I can show you. I won't show it to you all, but I'll show you the sound that the inner solar system makes as of now. Okay, so what I'm going to do is I'm going to click on this, and hopefully this will come through the speakers. So what you're going to hear is the bland sound of the radial velocity reflex waveform that the sun executes as a result of the inner planets going around the sun. So let's see if we can hear that. Yeah. It's not a very interesting tone. I'll play it one more time. What you're hearing is the two orbital periods of Earth and Venus basically mixed together, and you're hearing a very stable, very boring, very constant tone, right? And that's indicative of the fact that the inner solar system is not doing very much. You watch that movie, the planets just went around and around and around, the orbits didn't change, and so when that is sonified, there's very little of interest. You're hearing the two major planets in the inner solar system being against each other. Now, something that you can do, which is kind of fun, is if the planets become more massive, then they will pull on each other more strongly. And the orbits will no longer be so orderly. What I'm going to do is I'm going to open up a version of the solar system in which I've taken Earth and Venus and I have increased their masses so that their masses are slightly more than the mass of Jupiter. All right, so I've given this huge boost to the masses of Venus and Earth, and I'm going to ask what would happen to the inner solar system if that was the case. First of all, I can go to the actual graph and see what happens just using the graph. I have to just get this thing so that it... You know, it's funny, I don't get nervous talking in front of audiences, but it's amazingly kind of nerve-wracking to actually do computations in front of audiences. But there I got it to go. So let's watch what happens to Earth and Venus if they are given masses that are similar to Jupiter. I'll start that off. You can see that those two planets are not happy with each other. Right? They get into sort of spats, and then they kind of like find a new sort of slightly unstable equilibrium. And you can see that their eccentricities, the shapes of their orbits, are kind of vibrating all around. And so the interesting thing is, what would that sound like? If you sonify the planets sort of going nuts, then you can start to run into some very interesting kinds of sounds. So let's see what that sounds like. This Earth-Venus 390 .wav corresponds to taking the inner solar system and boosting Earth and Venus's masses by a factor of 390. Now, that sounds like a huge amount, but we find many solar systems out there in which planets with orbits similar to Venus and Earth have masses that are that large. So it's not that unreasonable to imagine a solar system, an alternate solar system that worked like this. So let's just recall what Earth and Venus sound like just with their ordinary masses. Let's just recall that bland, boring tone very briefly. Now, it's kind of interesting, like, before you've heard the sounds, like, what do planetary systems going unstable sound like, right? So before I play it for you, it's kind of interesting to imagine, like, what kind of sound am I going to hear? It was very much what I had in my mind. No one had ever thought of doing that. No one knew what the sound of a radial velocity waveform for a star with a planetary system that's going unstable would sound like. And so here's what it sounds like when you crank up the mass by a factor of 390. Oh, it's not that different, right? So you would think, oh, well, that's not very exciting. But we saw all that action. Let's just try cranking the mass up by a factor of 400, going from 390 to 400, and see if that changes anything. So that's a very different sound, right? So it's like the borderline of sort of dramatic instability for the solar system occurs when you move the mass of Venus and the Earth from 390 times their current values to 400 times their current values. Cranking it up to 450 makes things even more interesting. It's crazy, right? The planets are just like sort of crazily oscillating. We know of some other solar systems that are very close to being on the brink of instability. And so it's sort of interesting to hear what they sound like. I'll just play two examples that sound kind of good. And then this system right here, what's going on there is you have two planets which get into an interchange with each other, start to affect each other's orbits, changing angular momentum and energy back and forth, and finally one of them gets ejected at the end. Sort of that last sort of upward hum is the inner planet getting driven to a higher and higher and higher eccentricity as the outer one is ejected. So there's lots of interesting sounds. There's also planetary systems that are what we call in resonance. That is, their orbital periods are harmonics of each other, and they produce sounds that can be quite pleasing. Here's an example of what I'm talking about. This is a resonant planetary system. That has a much more musical sound to it because the orbital relations are much more there's much more harmonic content than there is in our own solar system. Okay, so now what I want to do is I want to go back to my PowerPoint presentation and pick up where we left off with Isaac Newton. Now, Isaac Newton was one of the great minds of all time. He very badly wanted to understand what would happen to the planets. He wanted to understand whether the planetary orbits were stable in the sense that they will keep marching forward uniformly in time. And he wanted to understand why Jupiter and Saturn seem to be moving apart over thousands of years. And he tried extremely hard to solve the problem, and he couldn't do it. And he wrote to one of his correspondents, he wrote to consider simultaneously all these causes of motion, and to define these motions by exact laws admitting of easy calculation exceeds, if I am not mistaken, the force of any human mind. Right, so that's a big deal. If Isaac Newton says that solving the problem exceeds the force of any human mind, then yeah, it's a great challenge, right? And so this became the obsession of the mathematicians of the 1700s. And the problem that they were interested in, they wanted to know, is the solar system stable? Newton was actually of the opinion that the solar system is not stable. And the way he proposed solving the problem was to hypothesize that every few thousand years, God comes in and resets the planetary orbits in a way that allows them to go forward. Newton saw the stability of our solar system as proof positive of the existence of a benign deity. Right? So he made this sort of tremendous attempt to solve the problem, gave up, and said that I'm going to leave it in God's hands. In the 1770s, one of the great French mathematicians came very close to solving the problem, and indeed thought that he had solved it. Again, this transparencies are not very bright. I went to the Lick Observatory Library and got the original manuscripts of Laplace, and I went to the particular page and found the particular formula which allowed Laplace to understand perfectly, to his precision, the motion of Jupiter and Saturn. It was an enormous success of mathematics that Laplace was able to do this. He was able to solve a problem that had completely eluded Newton. And so, as a result, he was so invigorated that he posited what became a very dominant philosophical sort of point of view for this, especially for the 1800s, and that is the idea of Laplacian determinism. Laplace felt that if you knew the positions of all of the particles in the universe and you were a perfect calculator, you would be able to predict the future with perfect accuracy. That is, if you knew what all the particles in your brain were doing and what everyone else's brains were doing, you would be able to see perfectly into the future. This idea is called Laplacian determinism. And Laplace also, from a philosophical standpoint, took the completely opposite point of view to what Newton did. Laplace felt that because he had solved these equations and had seen how the solar system works, that it was clearly there was no need for divine intervention, and by extension, no need for a deity at all. In fact, Laplace had a meeting with Napoleon where he explained the mechanisms that he had found for how the solar system works, and Napoleon was quite perturbed, and he was saying, but where does the Creator come into this? And Laplace famously said to Napoleon, he said, "Sir, I have no need for that hypothesis." And what he meant there was that everything unfolds without any sort of guiding hand. And so we see the pendulum going from Newton's view of sort of a God-operated universe to Laplace's view of this completely mechanistic, explainable by science system of the world. So Laplace claimed that the solar system would be stable for all time. But in these equations here, which thankfully you can't see very well, there are approximations. There are approximations built into the equations that are covering this screen. And by the 1840s, it was clear, this is Leverrier, who was the discoverer of Neptune, it was clear that the equations that Laplace was using were not accurate enough to predict the motion of the planets more than, say, 10,000 or 100,000 years into the future. They were perfectly adequate to explain the observations of the day, but as the observations became better and better by the 1850s, it was clear that Laplace's approximations were starting to break down. And this, of course, led to quite it was a big deal, because Laplace and Newton had both been involved in this problem, and in some sense, it tied together the whole fate of the solar system. You would really like to know, are the planetary orbits going to be stable, or is the solar system going to go haywire at some point in the future? And so in the 1880s, King Oscar II of Sweden and Norway announced that there was going to be a contest. And the contest was that if you could prove the stability of the solar system, if you could show that the solar system was either stable or unstable, it was stated in a slightly more technical way than that, but if you could mathematically make that determination, then you would win a prize of 2,500 crowns and a gold medal. And so, what could be better? There was the 2,500 crowns, the gold medal, and then this marquee problem, and then the great names of Laplace and Newton all thrown into the mix. And so there were a number of entries, and the winning entry was submitted by Henry Poincaré. And what Poincaré showed was that the problem is not solvable in the sense that the people who had put it forward were anticipating. What Poincaré showed was that even if you have just 2 planets orbiting a star, then you cannot write down a perfectly accurate solution that's good for all time. And what Poincaré had discovered was what we now think of as chaos. So you've all heard of the butterfly effect. If you have a butterfly that flaps its wings in Brazil, then a few weeks later, the tiny but ever-increasing effect on the air currents causes a hurricane which would have missed land to strike land. It causes, over a period of a few weeks, it causes the weather to be entirely different than it would have otherwise been. Our world is governed by a set of equations for which a tiny, tiny change in the initial conditions leads to enormous differences down the line. And that tiny, tiny susceptibility to tiny changes makes it effectively impossible to get a perfectly accurate view of what will happen into the future. This idea now is very much enshrined in thinking, in science, but it was radically, radically new at that time. Poincaré wrote a wonderful book called Science and Method in 1908, in which, for the first time, he really lays out the fundamental ideas that are inherent in chaos theory. This now is very much informing our current scientific outlook, and so it's very interesting that this problem of the stability of the solar system has sort of touched on 3 different fundamental sort of philosophical outlooks. There's the idea of a benign deity, the idea of perfect rational determinism, and then the idea of chaos theory. These all 3 have stemmed from this problem of the stability of the solar system. But that doesn't give us the answer, right? We still want to know, well, are the planets going to go unstable? What we know now is that we can only ask that question in statistical terms. We can ask the question, what are the odds that the orbits of the planets will be destabilized within, say, the next 5 billion years? That's a question that we can ask and hope to get an answer to. So the question is how do you get that answer? The way that you get that answer is to use a computer. So this picture right here is a picture of an orrery. An orrery, a classical orrery, this one was taken from the Paris Observatory, is a mechanical contrivance, clockwork, that allows you to sort of turn a crank and march the planets forward in their orbits. You can do the same thing with a computer simulation. Computer simulation understands the laws of gravity. The computer is very fast. The computer can march the planets forward in their orbits, just like I was showing with the software. And computers are fast enough now that you can march the planets forward, not just for 10,000 years, like I was demonstrating, but for literally billions of years into the future. It's possible to march forward, or as we say, integrate the planetary orbits for the entire future lifetime of the solar system. It is possible to compute a possible future for the planetary orbits. Now, of course, if you compute that, it's just one out of a huge number of possible trajectories. So each time you do a computation into the forward, you're sampling one of the possible futures. And so in the last few years, I became very interested in doing that. And I and my students use computers to march the solar system forward for long periods of time. This graph right here shows the solar system, and in particular the eccentricity of the Earth, that is the shape of the Earth's orbit, over the next 20 billion years. All right? Now, this is something of a moot point in the sense that in about 6 billion years, the sun is going to swell into a red giant. It will destroy Mercury, it will probably destroy Venus, and it may destroy the Earth. The Earth, as the sun swells into a red giant, it has this terrible wind coming off of its north and south poles, and the sun actually begins to lose mass. As it swells up and grows much brighter, it begins to lose mass. And as it loses mass, the Earth's orbit starts to creep outward. And it turns out the simulations of how the sun will die show that the sun expands at exactly the right rate that the Earth is creeping outward. And so it's not clear, it's fully not clear whether the Earth will survive and end up as a baked cinder when the sun is done with its red giant phase, or whether the Earth will actually spiral in and be destroyed by the sun. It's completely up in the air. Mercury will certainly be destroyed by the sun. But in any case, if the sun did not misbehave, this simulation is suggesting that the Earth would go on with no problem for tens of billions of years. But interestingly, this, of course, is just one of the possible future trajectories. This is a technical slide, which I'm not going to go through in detail, but suffice it to say that we did other calculations. We did additional calculations, and we saw something alarming. In some of them, it appeared that the solar system could go unstable. And by that, what we mean is that the eccentricity of Mercury over a time scale of hundreds of millions of years sort of bounces up and down and then suddenly goes nuts. It turns out that there's something intrinsic to the mechanism of the solar system that occasionally allows Mercury to suddenly go from having its eccentricity of 0.2 to an eccentricity of 0.6 or 0.7. And when that happens, Mercury's orbit crosses the orbit of Venus. Either Mercury and Venus collide, or Venus gives a gravitational boost to Mercury, which causes the inner solar system to go even more haywire. In this particular calculation, Mercury going nuts causes Mars to suddenly leave the solar system. And so we were amazed, right? We came to the problem with the expectation that we would see nothing but stability. We felt that the solar system certainly is looking very good right now. You know, if you integrate it forward for the foreseeable future, for tens of thousands of years, for millions of years, nothing much happens. But then on this billion-year time scale, under the right conditions, things can suddenly go nuts. And so we became obsessed with this problem and looked in great detail at what was causing Mercury to get destabilized. And it turns out that what happens is that Mercury basically random walks into a condition where the rate at which its orbit is precessing, that is, the rate at which its orbit is being turned around the sun, not the planet, but the orbit itself is being turned around the sun, can get locked into a commensurability with Jupiter. Jupiter's the most massive planet in the solar system. It's very good at sort of pushing things around. And if Mercury gets into this trouble spot, then what Jupiter does is effectively produces a steady drag on Mercury's orbit that causes its eccentricity to just get larger and larger and larger until things go haywire. And we were amazed to find that. And then last year, the problem was finally completely solved by a French scientist, Jacques Lascar, and his collaborator, Michael Gastineau. And what they did was they did 2,500 times more calculations than we had done. They had an enormous rack of computers. They ran them for years and built up this enormous database of possible trajectories for the solar system. And the answer is that there's a 1% chance that the solar system will go unstable, that is, go crazy like the sounds that you were hearing before the sun turns into a red giant. And there's a 99% chance that everything will be all right for the next 5 or 6 billion years. So it was very exciting to finally see this problem solved after more than 300 years of speculation and all these sort of interesting twists and turns. Another very interesting aspect of this is that the stability of our solar system, the fact that our solar system has a 99% chance of remaining stable, actually requires the general theory of relativity to be correct. It requires that Einstein be right. If Einstein's equations were incorrect, if the gravity were exactly as Newton had theorized, without the small modifications that come from Einstein's theory of general relativity, then the chances for instability go up to more like 50%. So the general relativity, it turns out, it provides a very important stabilizing mechanism for the solar system. General relativity forces Mercury's orbit to precess at 43 arc seconds per century, and that keeps Jupiter from exerting an outsized hand. That is, it keeps Jupiter from getting Mercury into trouble in far more cases than it would otherwise. So that's the last slide that I have, and I'd be happy to answer any questions that you might have. Thank you. And actually, it's not the last slide that I have. I just remembered. So the question is everybody's heading for the exits. What would happen if the solar system goes unstable? What would happen? What would happen if a Mars-sized planet, namely Mars, crashes into the Earth? So this is a simulation showing, let's just do it again, the impact of Mars hitting the Earth. And what you're seeing here is unfolding over a time period of a few hours. Right? So if you have Mars slamming into the Earth, it's terrible. The entire Earth is melted. It has a silicate atmosphere. And interestingly enough, we believe that this is what happened in the very beginning years of our solar system, something like 10, 20, 30 million years into the initial history of our solar system. There was a fifth inner planet in the solar system. That planet had roughly the size of Mars, we believe, and its orbit and the Earth's orbit were unstable relative to each other. That object slammed into the Earth. This is a simulation of that impact of that Mars-sized object hitting the Earth, and that's actually what led to the formation of the moon. And so kind of bringing it back to that very first slide that I showed you, had that crescent moon. It appears everything is completely calm, stable, yet the very existence of our moon stems from one of these instabilities that occurred in the very early phases of our solar system. So that is my last slide. Thank you.
So we want to thank Dr. Laughlin for both his excellent lectures. We want to now encourage people to ask questions.
Yeah.
I have a question about numbers.
Yes.
And I've been fantasizing about presenting this to an ace astronomer for many years. And it has to do with the Big Bang,
yes.
The numbers in the Big Bang. And I have here, it says the earliest moments of the Big Bang.
Yes.
The first stage is 10 to the minus 35th seconds.
Yes.
Then the thing slows down to 10 to the minus 30th second.
Yes.
Then it slows further to 10 to the minus 11th. And then finally 10 to the minus 10th, 10 to the minus 5th, then 0.01 to 300 seconds, and then finally 380,000 years, which I'm even skeptical about. My question is, what have you guys been smoking?
What was it, Proposition 18? Yeah, I agree that to, sort of from the outside, those numbers seem rather strange and arbitrary. And to flesh those numbers out and make them convincing to the point where you should be willing to accept them takes a full lecture of its own. Suffice it to say that if we look out into space, we see that the galaxies, the further away the galaxies are, they're all expanding away from, apparently from our point of view, right? As we look further out into space, we see galaxies with larger and larger redshift. And so if we imagine playing the clock back, right, the galaxies, instead of expanding from our location, are all coming toward our location, right? So if we imagine playing the clock back, taking all those motions and reversing them, then it's very clear that if you go back something like 13 billion years into the past, then the current state of the universe suggests that everything was very, very close together. The idea there of all the galaxies coming very, very close together, you can study how things behave when matter is packed very, very tightly together. That's what goes on at CERN, inside a super collider, inside a particle accelerator. You look at how matter behaves under extraordinarily high temperatures and extraordinarily high densities. And we believe the entire universe was subject to those conditions at a time 13.7 billion years ago. By using that line of reasoning and an enormous amount of sort of substantiating evidence from various areas in physics, you can put together a timeline that has those numbers to the sorts of accuracies that you were quoting that is quite believable from a scientific standpoint. So obviously, I have to stand up here and assert that. I cannot sort of defend the entire logic that goes into Big Bang cosmology in an answer to a single question. If you're interested, I urge you to read our book. I urge you to read Andrew Fracknoy's book and find out for yourself. It's something that is worth looking into.
Wait. Let's go on to
Oh.
let's go on to the next.
Yeah.
Well, your last answer didn't seem too convincing, but perhaps I've
was-
been wondering, why does the same side of the moon always face the Earth? That seems extremely unlikely.
So that would be very unlikely from an a priori standpoint. The moon is subject to a frictional tidal force, which causes the lowest energy configuration to have the heavier side of the moon facing the Earth and having the moon spin once on its axis per trip around the Earth.
Exactly forever.
Yeah, this question is exactly the same as I come in and there's a bowl sitting on the table and there is a marble, and that marble is lying exactly at the bottom of the bowl. Is that remarkable? It's not remarkable because if you set the marble in motion, it will roll back and forward, it will dissipate energy and will come to rest at the lowest energy configuration, at the bottom of the bowl. The Earth-Moon system, the moon has done that. The bottom of the bowl, effectively, for the moon is the state where its densest side is tidally, synchronously locked to the Earth, in the same way that the state for a marble in the bottom of a bowl, once it's dissipated its energy, is the bottom of the bowl.
Okay.
Okay.
The moon is leaving the Earth at the rate of 1 to 2 centimeters per year. What impact does that have for life on Earth?
So right now, the reason as the moon is going outward, that energy that is allowing the moon to slowly spiral outwards is being tapped from the spin of the Earth. So the Earth's day is getting slightly longer all the time, and that energy of rotation is being transferred to the moon's orbit. The effect for life right now is very small. Eventually, at around the same time that the sun is starting to have problems turn into a red giant, the moon will be much further away. There won't be solar eclipses anymore. And if the sun didn't turn into a red giant, the moon would eventually become synchronous with the sun and the Earth, and then eventually would actually come back in and crash into the Earth. But that won't happen as a result of the sun's future evolution. So I guess the short answer to that question is the slow tidal evolution of the Earth-Moon system has very little effect on life on Earth now.
Hi. The Hipparchus mission measured the motion and behavior of the stars, and some folks have looked at that data and estimate that Gliese 710 will pass fairly close to the Earth. Have you studied that? In about 1.5 million years, I think it's supposed to come by.
And how close is it supposed to come, like half a parsec?
There's a couple estimates. I can leave this with you. It's 1.2 parsecs or something.
1 or 2 parsecs. So the closest star to the sun right now is the Alpha Centauri system, Proxima and Alpha Centauri A and B. And they are about 1.24 parsecs. They're actually coming closer. So they'll, in I think 25,000 years from now, they'll be a little less than 1 parsec from the sun. Gliese 710 is probably coming in with a fraction of a parsec.
Right. Okay. One estimate was 1.1. Babilev, the Russian, estimates maybe 0.21 parsecs.
0.2 parsecs. So 0.2 parsecs is something like 30,000 times farther from the sun than the Earth is. And so that passage won't cause any significant perturbation to the solar system. Now, that's just Gliese 710. Over the next 5 billion years, we can expect much, much closer encounters. You can compute the odds, and I did compute the odds, and it turns out that there is about a 1 in 100,000 chance that the Earth will be ejected from the solar system within the next 5 billion years as a result of a close encounter with a nearby star. There's also a 1 in 3 million chance the Earth will get captured into orbit around another star. If that star is a red dwarf like Gliese 710, then we could be set for the next 2 or 3 trillion years. But you've got like just a 1 in 3 million chance of that happening. Yeah.
It was about 20 years ago when I was sitting in the auditorium at NASA Ames, and they had a little man talking that was quite a bit shorter than you are. And he was speculating on the moon and things. His name was Velikovsky.
Velikovsky?
Can you comment?
They let him into Ames?
They sure did. They're very
so
open-minded.
yeah, so Velikovsky wrote some books, I believe in the 1950s.
They're very open-minded at NASA Ames.
Absolutely. And one of those books is called Worlds in Collision. So Worlds in Collision was not based on the same kinds of ideas that I was putting forth here. It was sort of more of, shall we say, an ad hoc theory. Speculations that led to sort of similar results as what you've seen. But I think that's so far outside the sort of current thinking that it's been pretty much discounted. I like the title, though, Worlds in Collision. It's a great title for a book.
It was an entertaining talk.
Yeah, I could quite imagine.
How long will it take for the sun to turn into a red giant?
So the sun will be a full-blown red giant in 6 billion years. On the way to becoming a red giant, the sun slowly increases its luminosity. So 1 billion years from now, the sun will be about 10% brighter than it is now. The current climate models suggest that will cause serious problems for the Earth's climate. But as far as becoming a full-blown red giant, it's 6 billion years into the future.
Thank you.
Hi. In the 1% chance in your simulation that the solar system's orbits go haywire, that was attributed to the fact of Jupiter having an effect on Mercury.
Yes.
Would it not be more probable for that to happen with Jupiter having an effect on Mars or Earth, which is a larger mass and closer, if you think?
That's a good question. It turns out that it is Mercury's natural precession rate that is close to Jupiter's natural precession rate. And it's that similarity is what allows Mercury in this 1% of the cases to get into trouble. Venus and Mars and the Earth basically affect each other's orbits in such a way that Jupiter is unable to get a foothold on them. So they basically present a constantly moving target, and Jupiter, this is sort of a loose way of speaking, Jupiter is not able to influence Venus and the Earth directly in the way that it is able to influence Mercury. It's an oddity of the way that our solar system is set up, that this is the particular Achilles heel that we have, our particular mode of instability to which we're subject involves Mercury and Jupiter.
Is it possible for the moon or any other planet's moons to go act like Mercury and raise an eccentricity and go haywire?
So the answer to that is it appears that the solar system is extremely stable, other than this small probability that Mercury will go unstable. So the answer appears to be no, to a very, very high degree of approximation.
Thank you for a wonderfully accessible talk tonight. Easiest question. Some of your early slides, you showed the orbits of inner planets, and half of them were blue and half were green.
Yes.
Why?
Yeah, why? So the solar system is not in a perfect plane. And so what that showed was relative to the Earth's orbital plane, the green indicated when the orbit was above that plane, and the blue indicated when it was below that plane. So it was just a way of showing the orbital inclination on a two-dimensional plot.
What would happen to Earth after the sun turns into a red giant, if it doesn't get destroyed?
So Earth will get hot enough so that all the water in what we call volatiles will be lost to space. And so Earth will become basically a kind of a lava ocean planet. Then when the sun turns into a white dwarf and cools down, then the lava will solidify. Interestingly, the Kuiper belt in the outer solar system will still be out there, and the Oort cloud, which has the comets, will also still be out there. And so there will be some cometary impacts onto the Earth, and so you'll get a little bit of water back from comets. Geology will continue to go on, volcanism, right, because the Earth was totally melted and it'll take a while to cool off. So I think you will basically have the evolution of a kind of a lifeless planet, with geology without biology is, I think, what will happen.
I have what may be a complicated setup for what I hope is a simple question. Thinking about what you're talking about and thinking about possibly sort of running it backwards to the early solar system and these sort of very nonlinear effects you were talking about with the orbits, do you see in the early solar system changes in orbits due to sort of latent mass that gets accreted to planets and mass of planets shifting, or is it for the most part just blown off during the ignition of the sun?
Yeah, so you can't use this technique to walk backward in exactly that way, but you can look at the geologic and especially the isotope evidence in the planets themselves. And so it is clear that late stages of accretion, where the moon-forming impact was the best example, did play a major role instead of kind of setting the final initial conditions for the solar system that we have today. So first few 100 million years, there was a lot going on. And then things calmed down, and we're in this long phase of very stable evolution.
What determines the eccentricity? Is it just the force of gravity?
Yeah, so that's a good question. The eccentricity is determined by if you take the planet at its closest approach to the star, The eccentricity is determined by how fast it's going. If it's going at exactly the right speed, then it just stays in a circular orbit. If it's going too fast, then it boosts out to an eccentric orbit, and if it's going too slow, then it plunges down into an eccentric orbit. So it's the exact balance between distance and velocity, that is how much angular momentum you have, which determines your eccentricity.
If Mercury crashed into Venus, how would that affect Earth?
So that would not be as bad as if Mercury crashed into the Earth, but it would be bad, and the reason why it would be bad is because that would send a whole spray of sort of asteroid-sized bodies into the inner solar system. Some of those would inevitably strike Earth, leading to these kind of mass extinction events. So it doesn't destroy the Earth, but it's not good news if that happens.
Hi, I was just wondering what your opinion was on the sort of duality seen in the certainty and stability of the large-scale universe and the chaos seen in the frontiers of, say, quantum mechanics, and whether you believe one is more scientifically valid than the other.
Well, so as you go to larger and larger scales, quantum effects become harder and harder to see, right? The laws that govern the kind of physics, intuitive physics that we're used to, Newton's laws work great. But then when you go down to the scale of electrons, then quantum mechanics becomes dominant. Uncertainty is built into the quantum mechanical structure of nature. But then when you get very, very large numbers of particles together, sort of the statistics of large numbers take over and give the illusion of very uniform and predictable evolution. So I guess that would be my answer to what's a very, very good question and a very deep question.
Thank you.
Has your analysis accounted for other galaxies approaching ours within the 5 billion years? Because I thought that we were on a collision course with some
Andromeda.
other galaxy or
Yeah, so we're on a collision course with the Andromeda Galaxy, and we're going to collide with the Andromeda Galaxy sometime in the next 5 billion years. And that is dramatic on the large scale, but on the scale of the solar system, nothing really happens. The number of stars in the night sky increases by about a factor of 2. Stars are like sand grains separated by miles, right, if you make that analogy. And so doubling the density of stars doesn't affect the dynamics at the solar system level. So it's exciting on the global scale, but it doesn't really affect the evolution of the solar system at all, the fact that we're on this collision course with Andromeda.
So you were mentioning this Gliese or something?
Gliese 710, which will make a passage of something like 30,000 Earth-Sun distances away. Those passages are brief enough and sort of low impact enough so that they don't have a significant effect on the planetary motions.
Is that from Andromeda or from our own galaxy?
Just from the stars that are continuously passing through the solar neighborhood. So Andromeda will simply inject another factor of 2 of stars into our solar neighborhood. And so, we're just randomly getting these ever so slight perturbations from these, they're like ships passing in the night at large distances. But we're very unlikely to collide with any of them.
Thank you.
What would happen to the moon when the sun turns into a red giant?
So that's a good question. Again, that depends on whether or not the Earth survives. So in the case that the Earth doesn't survive, the moon will also spiral in. In the case where the Earth and the moon both survive, then I believe eventually the moon will spiral out to a maximum distance from the Earth, where the Earth and the moon will both be spin synchronous. So the Earth will always show one face to the moon, and the moon will always show one face to the Earth. Then very, very slowly, that system will get spin synchronized with the sun's white dwarf. And what will happen is the moon will slowly come in and will eventually crash onto the surface of the Earth. That's the answer.
You didn't really talk about what will happen to Saturn and the other planets?
Saturn, yeah, no, Saturn. The outlook for Saturn looks pretty good. Yeah, you know, Saturn will warm up so that it's about the temperature of boiling water, but it's all right. That's okay. We know of planets that are much hotter than boiling water, and then the sun will turn into a white dwarf, and Saturn will cool back down. So Jupiter, Saturn, Uranus, and Neptune they're good to go.
About how many of the French scientists' 2,000 more experiments than ours are correct?
Oh, how many of the French scientists, 2,000, were what?
More experiments than ours are correct.
Oh, well, so all the experiments are correct. They just looked at a much larger sort of range of possibilities because they had a lot more computer power than I had. In fact, this computer right here was doing some of the calculations that I showed, and he had a whole supercomputer. So it was just like a different way of looking at the problem.
My question has to do with smaller solar systems, like you can think of Jupiter as its own little solar system. Has anyone looked at how the Galilean satellites would evolve around Jupiter?
Yeah, so the Galilean satellites have already evolved so that they're in a resonant configuration. And that resonance should be stable for at least 100 billion years. 100 billion years. Now, if you really wait long enough, then a passing star will eventually disrupt the Galilean satellite system. But then we're talking like quadrillions of years. So those, yeah, Jupiter, the outer solar system is a much better long-term prospect than the inner solar system. Excellent. But then when we're talking about billions of years, it just doesn't matter. Right?
Okay,
but
so we'll all be living on Jupiter or Saturn.
Yeah, we've got plenty of time to move there.
Why is the eccentricity of the inner planets of the solar system so low?
That's a good question. That has to do with the fact that the disk of gas and dust that gave rise to the inner solar system was in some sense relatively uniform. And we didn't have a planet that was more massive than Jupiter, a planet that was closer than Jupiter that could have screwed things up. We think that the planets that we're finding around other stars that have high eccentricities have those high eccentricities because they start out under much more crowded, in some sense, configuration than we started with. We started with a sort of nice quiescent planet-forming disk, and that led to a solar system where everything is working pretty well. We sort of had the idea that most solar systems would be like ours. We're now finding that that's not really the case. Probably only about 10% of solar systems are as stable and sort of low eccentricity orbits as ours are. It's interesting. And that's it.
Let's thank Dr. Laughlin. Thank you for not only an illuminating talk, but good advice on future real estate. We appreciate that. Thank you all for coming, for the great questions, and we'll see you in November.